In this video, we're going to discuss one of the key concepts in physics, which is angular momentum, and we're going to see how it plays an essential role in understanding Kepler's second law of planetary motion. Perhaps many of you are familiar with Kepler. He was one of the main figures of the scientific revolution that took place in the 16th and 17th century in Europe. At the time, Europe was just awakening from its long sleep during the Dark Ages, in which science wasn't, respected, and it was mainly ideas in theology and superstition that dominated the doctrine of thought in Middle Age Europe. In the 14th and 15th century, the Renaissance began in modern-day Italy from the city of Florence. And after a couple of centuries, the scientific revolution followed afterwards. Kepler is among many of the pioneers of our modern picture of science. And they were founders of the scientific method, along with Galileo, Copernicus, and the great master, Sir Isaac Newton. Here, I would like to look into specifically one of three laws of planetary motion, which were formulated between the years 1608 to 1619. And namely, we're going to talk about the second law, which is a bit simpler than the other two when it comes to the mathematical structure. And then in future videos, we will look into the first and third laws as well. Now, in this figure that I have on the left-hand side of the screen, it is an exaggerated, shape of the elongated elliptical orbit of Earth around the sun. We know from Kepler's first law that planets orbit the sun in not perfect circles, but rather in elongated circles, which we call ellipses, in which the sun is situated at one of the foci of these ellipses. Now, obviously, the eccentricity of the planets in our solar system is not large, meaning that their orbits are close to circles, but through rigorous observational astronomy that Kepler, he based his research on countless and endless nights of observing the stars. And in particular, he was looking into the orbit of planet Mars. And over the years, when he looked into the data, he realized that Mars and later other planets could not simply orbit the sun in perfect circles. And he came up with three geometrical rules, geometrical laws, discussing the shape of the orbits and how the planets move around the sun. Now, Kepler's second law states that the radial distance between the sun and the planet, such as the Earth, let's say, sweeps out equal areas in equal times, meaning that when the planet is further away from the sun, it moves slowly, and when it's closer to the sun, it would move faster. We should remind ourselves that Kepler lived before Newton, and we all know that before Newton, there wasn't a satisfactory and scientific explanation of the force of gravity. Later on, when Newton came along, he actually, with his universal theory of gravitation, was able to explain beautifully all three laws of Kepler. The only thing we should know in order to understand Kepler's second law is that the force between a planet and the sun is a central force. What do I mean by a central force? So I'll just write it down here. A central force is a force that acts along the line between a center of force, which we call the sun, and the planet. And it doesn't have any directional dependence. So it only depends on the distance between the sun and the earth, or to be more exact, it points towards or away from the center of force. Now, since gravity is an attractive force, the central force of gravity would, point towards the sun. If I want to analyze this problem mathematically, this is the way that we would represent the central force of gravity. Taking the sun to be the object that is exerting the force. So in vector notation, force of gravity would be given by a magnitude times a direction. And since it's an attractive force, it will be pointing towards the center of force. So if I want to show it, let's say at this instant, the force on the Earth would be pointing directly towards the sun. R hat is a unit vector that points away along the radial direction, and therefore we have this minus sign here to indicate that gravity is an attractive force. The exact shape of the magnitude of the force of gravity, as I said, was given by Newton. Before him, we weren't sure about what the mathematical relation was, but Newton taught us that the force of gravity has a magnitude that varies directly by the product of the two masses that are interacting gravitationally, and that divided by the square of the distance between them. But nevertheless, we don't need the exact mathematical formula of Newton's law of universal gravitation in order to understand Kepler's second rule. The only thing that we have to consider is that the forces that are playing the essential role in shaping the orbits of the planets around the sun are central forces in nature. All right, that being said, let's define the angular momentum concept in physics. And I'm going to look into the classical definition of angular momentum. So like always in all problems in mechanics, we always have to consider a frame of reference in which we can measure the dynamical variables in accordance with it. So here, let's say if I'm looking at a Cartesian system of coordinates x, y, z, and let's say I have a specific path in which a particle is moving along. Let's say the particle is, let's say, located at this point in some, moment in time. I can define the position vector of the particle with respect to this origin by a vector that connects the origin to the location of the particle, and I call it r. And the unit vector in the direction of this position vector would obviously be the vector r hat, which would point in this direction. So it's a vector of unit length and pointing radially outwards from the center of our coordinate system. And if I assume that my mass or my particle is moving, let's say, along this path from left to right, I can define its velocity as a vector that is always perpendicular. Oh, sorry, it's always, let's say, along the tangent to the path. It's in the direction of the tangent line along the path. So I'll draw it like this. And this would be my velocity. Right. Now, given these two quantities, I can define what we call linear momentum. And the linear momentum of a particle, we usually show it by P. It's a vector that is defined as the mass of the particle times its velocity. So this is called linear momentum. So anything that has mass and it's moving would have linear momentum. And angular momentum is defined by the position vector cross-producted into the linear momentum. So this is called angular momentum. And since it depends on the location of the particle, we usually say this is angular momentum with respect to this position vector, which goes, which is defined with respect to the origin of our coordinate system. So the angular momentum really depends on our origin, whereas the linear momentum is just the product of mass times velocity. Now, since angular momentum is defined as a cross product between the position vector and the momentum vector, that means that angular momentum is always going to be perpendicular to the plane that is defined by the position vector and the momentum vector. Note that the momentum vector is always in the same direction as the velocity vector. So if I have a particle that in general it's moving in a different direction than its position vector shows, then it would have a non-zero angular momentum, as the position vector and the velocity vector may be completely independent, linearly independent vectors, and therefore I can define my angular momentum to be actually perpendicular to both through a cross product. We all know from vector geometry and linear algebra that the two vectors that are not collinear, they actually define a plane. So let's say here R and V are not collinear. As you can see, they form an angle in the two-dimensional plane, and thereby I can draw, or I can define their cross product as a vector that would be perpendicular to the plane. On the other hand, if I were to find out what the size of my angular momentum is, again, from linear algebra and vector geometry, we know that the magnitude of the cross product between two non-collinear vectors would be the area of the parallelogram that is made by these two vectors. So if I consider a parallelogram here that is formed by vectors R and V, so roughly parallelogram. This parallelogram would have an area which is exactly equal to the magnitude of the angular momentum, which we show by L. So this is how angular momentum of a particle is defined with respect to some origin. Now, what does this have to do with our Kepler's second law? We'll get to that shortly. But one important feature that we would like to discuss is that for central forces such as the force of gravity, our angular momentum would remain constant. In other words, it wouldn't change in time. Now, in order to understand how angular momentum depends on time or how it would change with time, all I need to do is to take its time derivative, and I'll do that right here. So the time derivative of my angular momentum is given as the time derivative according to its definition of r cross p, r cross the linear momentum, and that would be given as dr dt cross p plus r cross dp dt. Now, the derivative of the position vector with respect to time is what we call, or how we define, the velocity of the particle. And on the other hand, the derivative of momentum with respect to time is given by Newton's second law as the net force on the particle. So the time derivative, or the rate in which my angular momentum changes with time, is actually the velocity of the particle times, or to be more precise, cross-producted into its linear momentum, plus the position vector of my particle or my object cross-producted into the force. All right, the first term can be easily shown that it would be zero. The reason for that is obvious. The only thing that we have to do is to consider the definition of linear momentum, which is just mass times velocity. And here I see that this can be written as mass times velocity cross-producted into itself. And any vector cross-producted into itself would be zero. The reason for that is that a vector with itself cannot define a plane, or a vector is linearly independent from its, is linearly dependent to itself. Right? In other words, there wouldn't be any parallelogram, so therefore the size of my angular or cross product, whatever the result is, would be zero. So the first term turns out to be zero, and we end up with an equation that is that you can shows up in many texts and in classical mechanics, and that is that the time rate in which the angular momentum of an object changes is actually the cross product between the force on the object and the radial vector, or the position vector. Now, this cross product, I'm sure you're familiar with it. We give it an independent name in physics, and we call it the torque, or the moment of force. So at the end of the day, we end up with an expression that the time rate in which the angular momentum of an object changes is always equal to the torque, or the net torque, on the object. Now, what does this have to do with Kepler's second law? And as I said, if we consider the forces to be central in nature, such as the force of gravity is, I can actually see from this equation that the angular momentum will not change. So here, I would write down this r in terms of r times r hat, right? The size of r times its unit vector. And the force here, which was the central force, earlier we saw, can be written as minus F times r hat. So in the case of a central force, for central forces, such as gravity, dl dt can be written as minus r F r hat cross r hat. And since again, we have a vector cross multiplied it by itself, it would be 0. In other words, for central forces such as gravity, the time derivative of the angular momentum of the object would be 0. And this actually indicates that the angular momentum must remain constant. And since the direction of my angular momentum is always perpendicular to the direction or to the plane that is, made by the position vector and the velocity vector, if this were to remain constant as it would be for central forces, that means the orientation of this plane would be constant. In other words, the plane of orbit of my planet around the sun, the plane of orbit of the planet around the sun would remain fixed. Well, that leads us to consider the dynamics to be essentially explainable by a two-dimensional coordinate system, because you see the plane of orientation would not change in time, so I can forget about the third dimension and just consider this as a two-dimensional problem. All right. Now we're in a position to explore or to derive Kepler's second law of motion. And in order to do so, what I would do is I will draw another ellipse just to make things consistent and simple. So let's say, think of this as roughly being an ellipse. And here's the center of force, which is located at the focal point of, or let's say at the foci of one of the foci of my ellipse. And let us look at the position vector and see how it changes over time. So let's say if the planet is at some moment of time right here, let's say at time t, then the position vector would be given as r as a function of time t, because generally the planet will be moving. And at some later time, let's say if it's orbiting in this direction, the planet would come to another point, and the position vector would point in a different direction. It would change both in general, both in direction and in magnitude. So if I want to find out the infinitesimal changes in my position vector, what I would consider is I would consider a very, very tiny infinitesimal time that has passed between these two locations here. So if the planet was at this location at time t, I would consider it to be at this location at time t plus an infinitesimal time interval, which I would show by dt. During this infinitesimally small amount of time, the planet has covered, or let's say has swept this area here, which is defined between the distance between the planet and the sun, and its let's say path along its orbit. So we can see that there's this tiny area here, which is swept out by the planet in this short, infinitesimally small amount of time. We'll call this little area EA, and from vector geometry, again, we know that area is a vector in nature, and the magnitude of the area would be obviously the surface area of the shape that we're discussing, and the direction of my area is always going to be perpendicular to this to the surface area. In other words, the direction of my area, my infinitesimal area that has been swept out by the planet, would be along the same direction as the angular momentum of the planet. Right. So that being said, I'm going to find out an expression for this little infinitesimal area that I have here. Now, if I zoom in a little bit, I can actually consider this area to be, in a way, it looks like a triangle. It can be estimated by a triangle. And the reason for that is the fact that the time that I have assumed to be passing while the planet is making this tiny distance is infinitesimally small. It's dt, it's infinitesimally small, so the actual path in which the planet takes in this infinitesimal time would be very, very similar to a straight line. Remember, we're talking about infinitesimally small quantities. So they're not finite quantities, they're infinitesimally small quantities. So therefore, the curve on the orbit is would be exactly equal to the straight line segment. And therefore, I can actually calculate the area. But on the other hand, we know that the area in linear algebra, geometrical, and vector geometry, the area is actually given by the magnitude of the cross product between the two vectors, which is the area of the parallelogram. And obviously, the triangle that we see here is half of the area of the parallelogram, right? So here I can consider the, in this figure here, I can consider this little infinitesimal area to be 1/2 of the cross product between the position vector in these two different time periods. So let's just don't forget to mention that the position vector at an infinitesimal time after this point in time would be r times t plus dt. Okay? So the bottom line here is that I can write down the infinitesimal area that is swept by the planet in this little tiny amount of time as being 1/2 times the magnitude of the cross product between the position vector at time t and the position vector at time t plus dt. Okay, and as I said, generally the position vectors at different times will not be collinear. So we have this area here, and we can define the area of a triangle to be actually half the area of the parallelogram that is being formed by the two position vectors. Okay, now the rest of this would be a simple mathematical calculation that I can express this r, the position vector, at some later time in terms of the position vector at some earlier time using a Taylor expansion. Now, since we're talking about infinitesimals, I can see from the Taylor expansion that I can only use the linear terms. I can only take the linear terms and forget about the nonlinear terms. In other words, I can write this as an exact equality as r at time t plus that little amount of time that has been passed times the derivative of time of my position vector with respect to time. All right. The other terms which involve orders of dt squared and dt cubed here, dt cubed, and etc. We can neglect all of them and make this an exact relation. The reason for that, as I said, this is not a finite number, it's an infinitesimally small number. All right, now on the other hand, I know what this expression is. The time derivative of the position vector is what we call the velocity. All right, so going back to the area, I can write it as 1/2 times the magnitude of r evaluated at time t, cross-producted into r evaluated at the same time, plus v dt. All right. Let's now expand this cross product. So here I have r times t cross r at time t plus r at time t cross v dt. And we should also know that v is also evaluated at time t. It's the derivative of the position at time t. All right. Well, the first term, again, is obviously going to be 0 because it involves a cross product of a vector with itself. And we're left with the second term. So since I know that dt is always a positive infinitesimally small amount of time, because time always flows in one direction, right? It moves forward. So I can bring it outside the absolute value symbol. In other words, I can express the little area that is being swept by the planet and the time dt as 1/2 times the magnitude of r cross v, and bring out the dt since it's positive. Now, if I carefully look into this r cross v, I can write it down, or I can write it in terms of the angular momentum of the planet. Remember, the angular momentum was defined as r cross mv, right? So in other words, r cross v, which appears right here, can be written as the angular momentum per unit mass, or per unit mass of the planet. So coming back to our expression for the area covered, I can write it finally in this form. EA equals 1/2 times the magnitude of my angular momentum divided by mass times dt. Or in other words, I can divide both sides by this infinitesimal time period and come up with this result that the derivative of the area swept out by the radial vector, by the position vector of a planet, changes in time with this rate. Okay, this is a very important result. And since for central forces, we just proved that L is constant, that means the rate in which the area changes over time would remain constant. And this is the mathematical expression of Kepler's second law. Second law. Now I'll have to pause a little bit here and try to explain to you what this actually indicates. So this just tells me that the area swept out by the position vector of a planet in different parts of its orbit around the sun at equal times would be equal. In other words, Um, if I integrate this, you know, expression here, I can come up with the finite area swept out by the planet over a finite amount of time. And I can compare it in two different periods in the orbit of the planet around the sun. And let's say if the planet, during a time interval, which I would show by delta T1, sweeps out an area of delta A1, and later along in its orbit, at the time interval of delta T2, it sweeps out an area delta A2, then if delta T1 equals delta T2, that means the areas would also have to be the same. Delta A1 would be delta A2, according to the fact that this quantity does not change, right? So let's go back to our picture of our orbit here, and let's talk about the consequences of Kepler's second law that we just derived. So when the planet is further away from the sun, due to the weaker amount of gravity or the weaker gravitational force it feels, it would be moving a bit slower. And if the planet is closer to the sun, due to the increase of the gravitational force, it would be moving faster. But how fast or how slow would be given by Kepler's second law. In other words, the time it takes for a planet to cover a given, let's say, area around the sun would always remain constant. So here, since the planet is further away from the sun, it must move slower in order to cover the same amount of area as when it is closer to the sun, which would have to move faster. And, you know, if the orbit was a perfect circle, then the planet wouldn't speed up or slow down. Because in a perfect circle, the position vector would, you know, sweep out equal areas always in equal times, according to Kepler's law. And because of that, the velocity of the planet around the sun would be a uniform velocity. But in general, this is not the case, right? Kepler taught us through, as I said, rigorous data that he gathered by studying the planet Mars. He realized that its orbit had to be in the form of an ellipse. And furthermore, he also found that the position vector of Mars sweeps out equal areas in equal times. Sometimes Kepler's second law is called the law of areas for obvious reasons. Now, let me, point out an interesting fact. Have you ever noticed that the number of days of summer in the northern hemisphere is larger by a few days, 4 days, than the total number of days in winter? In other words, in the northern hemisphere, the summertime, if I count the days in summer in the northern hemisphere, I would end up with about 93 days. 93.6 to be exact, but let's consider it 93 days. And for winter time, the number of days is 89. Now, I'm not considering, let's say, leap years, in which we add one day, sorry, to the calendar in February, but forget about leap years. So on average, for the northern hemisphere, I should mention this, northern hemisphere, the summer time is longer in the number of days. There are more days in summer than in winter. We have 4 days more in summer than in winter. Have you ever thought about this? Why is this the case? And the fact is interesting. It's because that when it's summer in the northern hemisphere, Earth is at its farthest distance from the sun. Now, this can be a little bit tricky, contradictory. You would say, oh, if Earth is farther away from the sun, we should feel less sunlight and it should be colder. Yes, that is right, but that is not responsible for the seasons. When it's summer in the northern hemisphere, it's winter in the southern hemisphere. The reason for that is that the Earth's axis of rotation about itself is tilted, and it's not perfectly aligned with the direction of the angular momentum of its orbit around the sun. So that's the reason. And although on average, Earth is about 5 million kilometers away from the sun, further away from the sun in the summertime of the northern hemisphere than it is in the wintertime of the northern hemisphere. Therefore, it moves slower in the summertime. I'm talking about the northern hemisphere. So the Earth moves, when it's summer in the northern hemisphere, the Earth moves slower. Therefore, in order to keep satisfying Kepler's second law, it would have to spend more time to cover a given area than what it is doing in winter. So for the northern hemisphere, or let's say if it's summer in the northern hemisphere, the Earth is moving slower because it's further away from the sun. And when it's winter in the northern hemisphere, it would have to move faster. And therefore, the number of days of winter in the northern hemisphere is fewer than the number of days in summer. Okay, so I hope you've all learned something from this lecture on angular momentum and how it plays a role in Kepler's second law. You can see that this is a form of Kepler's second law. The mass of the object and the angular momentum is constant, right? Due to the central nature of our force, and therefore the areal velocity of a planet remains constant. dA dt, sometimes we call it the areal velocity as well. And this explains some familiar phenomena from our perspective, our point of view on Earth. Please feel free to leave your thoughts and suggestions in the comment section. I would love to receive your feedback. And don't forget to subscribe to my channel next time. We will return with looking into the other 2 laws associated to Kepler. So until then, take care of yourselves and bye-bye.